We've seen that differential equations usually have infinitely many solutions, but often in applications you're really only interested in one of those infinitely many solutions. There's often a particular solution that you would like to find, but if you have infinitely many solutions, you need to figure out some way of finding the one solution that you're interested in. So let's have a look at an example of that kind of situation. So let's find the solution to this differential equation, y prime minus 2y equals 4, the one solution that goes through this particular point, 2, 4. So we saw in a previous video that the general solution to this differential equation is y equals minus 2 plus a constant times e to the 2x. And remember, the constant parameterizes the family of solutions. So for any single solution to this differential equation, what will appear here is not a letter variable, but in fact just a number. So to get some idea of why there should be a solution that goes through this point, let's have a look at a graph of all of these functions. So here is GeoGebra set up with let me make this a little bigger. Here's GeoGebra set up with a graph of the solution, and as I vary this slider here, you'll see that this constant in front of the exponential changes. Right now it's 6. Right, I can make it bigger, I can make it smaller, I can make it negative, and you can sort of imagine that if this slider were infinitely long and infinitely precise, I could slide it back and forth so that this graph, I could make this graph land on any point in the entire plane, right? So we're looking for the solution that passes through 2, 4, so that's right here. So if this slider were infinitely precise, I could make this graph land on that point, and then I would know the value of c that I want. But the slider isn't infinitely precise, so somewhere between 0 and a quarter, there is a value for c that will make our solution go through this point. So using a slider like this isn't going to do it. We're going to have to find the appropriate value for c algebraically somehow. So let's see how we can make that happen. So this is the general solution, right? Which I haven't been writing the fact that it's a function, but remember, y is really a function of x here. And we want it to go through this point. So how can we express that this function is supposed to go through that point? Well, in the usual way. The x coordinate is the input, and the y coordinate is the output. So we can write this equation. This equation expresses the idea that our solution is supposed to be going through the point 2, 4. But remember, we have a formula for this solution. It's up here. We have a general solution to the differential equation, so we can plug 2 into there. But remember, this 2, this is an x value. So what we're going to do is use our formula for the general solution and plug in 2 for x. So we get minus 2 plus c. C is what we don't know yet. Remember, C parameterizes the family of solutions. Since we don't know which solution we want, it makes sense that we don't know c yet. So c times e to the 2 times x, and 2 is the x value that we're working with. So we get this equation. 4 equals minus 2 plus c times e to the 4th. And look at what we have now. This is an equation that where c is the only thing that we don't know yet. So we can solve this equation for c. So move the 2 over, divide both sides by e to the 4th, and we get c is 6 over e to the 4th. So let me break out a calculator and get a decimal approximation for that. So 6 times e to the negative 4th. There's my exponential button. And what I get here is approximately 0.1989 and change. Of course, this decimal goes on forever. So this tells us that the particular solution that we want to go through the point 2, comma 4 is minus 2 plus this awful number, 0.10989 times e to the 2x. So this is the particular solution that goes through our point 2, comma 4. In this particular example, there was only one solution that goes through that particular point, and that's actually a pretty typical situation. Unless the differential equation, well, I should say that's a typical situation for a first-order equation. Unless the differential equation has some weird stuff going on, a first-order equation will have only one solution that goes through any particular point. So let's have a look at another example of that. I should say that this situation where we have a differential equation and also some point that we want to go through, this is called an initial value problem. It's such a common situation that there's an abbreviation for it. Usually we will call this an IVP. So an initial value problem is a differential equation plus some data point that you want to get a solution through. And to solve the initial value problem, you'll find a solution to the differential equation that goes through the data point. Usually what you'll do is you'll find a general solution for the differential equation, and then you'll go through this process that we did here to use the data point to find which particular solution goes through the data point. All right, so let's look at another example of this situation. Let's solve this differential equation, y prime equals 2x minus 3, subject to the initial condition that y of 2 should be 1. Now I've put quotes around differential equation here because normally in a differential equation we expect to see the unknown function and its derivatives, but here we only see a single derivative of the unknown function y. So, officially, technically speaking, this is a differential equation, but this isn't a new sort of thing because y isn't on the other side of the equation. We can actually solve this equation just by integrating on both sides. If we integrate with respect to x, dx on both sides, or integrate with respect to x on both sides, on the left-hand side, the integral of y prime with respect to x is just y. And on the right-hand side, right, this is just an indefinite integral. We get x squared minus 3x plus a constant. Here is why it's so important to not forget your constant of integration. We sort of expect that a differential equation will produce a family of solutions, and here the constant of integration is now the parameter that parameterizes the family of solutions. If you forgot to write your plus c, you would only ever find one solution to this differential equation, and it would not be the one that you wanted, probably. So we found a general solution for this differential equation. Now let's apply the initial condition to find the particular solution that we want. So our initial condition is that y of 2 is equal to 1. This is called an initial condition even though the x value isn't 0. How you use the initial condition is the same whether the x value is 0 or not. So it just sort of gets called an initial condition no matter what the x value is. So the initial condition is that y of 2 is equal to 1. But remember, we have a formula for y that's right here. So we can plug the x value in there. 2 squared is 4 minus 3 times 2 is 6 plus a constant. So we get the equation 1 equals minus 2 plus c. And so c is 3. And so the particular solution that we want is y equals x squared minus 3x plus 3. And that's the particular solution that solves this initial value problem with the differential equation and an initial value.